So now that I have all that information, we can start solving our problem. First thing we need to find is PV and TV. Okay, so PV diagram, pressure, specific volume diagram. Pressure here, specific volume here. Remember, this is an isothermal. An isothermal, as we've seen in this previous video here, follows a shape like so, right? Because of the relationship between P and V always being, how can I say this? The multiplication of them always being related. So, we are going from a state of higher energy to one of lower energy. So I expect us to be going from here, somewhere here. But we can check, right? We can be sure. We know that our first specific volume, our first state is 0.109. So just use approximate values for now. 0.109. And for the second one, it's 0.0081. So for sure, we're going down on the scale here, 0.0081. All right. What about pressure? First state, we are at 2.5 megapascals. 2.5 megapascals. So we're over the way up here. 2.5 megapascals. And then for the second one, it's a saturated mixture, and we are at 16 megapascals. 16.5 megapascals. So going from 2.5 to 16.5. Okay, so this is our first state here. Let's combine these two. It's right here, first state. Second state is going to be right here. And let me just make sure that my line crosses the right spot. It's going to look something like this. This is hard to do. Got it this time. All right, got it. All right, so what we're doing is we're going for our PV diagrams is going to show something like this. Okay, and then to make it a bit better, what I'm going to do is I'm just going to put this a bit to the side here. I'm going to increase this a bit here. And that's going to allow me to put an extra piece of this diagram, which is the dome. Just to, let's see, this is 90%. This is superheated, so maybe like so. Dome's going to be something like so. Okay, so we know that we start at superheated, so outside the dome, and we're going in. At some point we cross the saturated vapor, and then we go on to the 90%, which is where we are at. Now, once we cross that dome line, the temperature and the pressure cannot change. So at that point, we need to be going straight. Okay, so I need to make sure that this isothermal goes like so, and then like so. So it's going to be this, and then we're going to stop right here. Okay, so state 1, state 2. That's going to be kind of the gist of this. All right, what else? That's the PV diagram. So we go on an isotherm path, and then we go back on the other one is TS. So temperature and entropy. And for this one, we know the temperature does not change, right? So we can be confident to put this as 350 Celsius, and we're going to have to stay here the whole time. Now, as for my entropy, we know that entropy on this guy here is 6.884, and then 5.06. Okay, so we can go ahead and say 6.84 here, and here we can go ahead and say 5.06. Obviously, these are approximately, and these are all in kilojoules per kilograms per Kelvin. Okay, so again, I can eliminate this for the case of the TS. I don't really need to, And all we're doing here is we're starting at this. We're starting at state 1 here, and we're ending at state 2 here. Okay, so that's what the TS looks like. All right. Next part of the problem. After drawing these diagrams, we're asked to determine the pressure when dry saturated steam exists. So this is super easy by looking at the PV diagram, right? Where is the saturated vapor? Saturated vapor is occurring exactly when it hits this dome line that I created, right? And that is, it has to be on the same pressure as state 2. Okay, so we can actually check this here. The saturated pressure is the 16,529 kilopascals, or approximately 16.5 megapascals. So that's our part B. Our part B is P2, no, not P2, P of the dry, what do you call it? Dry saturated steam of saturated steam equals 16.5. What was it? 29 kilopascals, which is approximately 16.5 megapascals. Cool. All right. Last, what is work? Right? Last piece of the puzzle is, what is work done in this system? So, and for that, we're going to use the first law, and it's we're going to use the first law in the form of the closed system, and we know that we have about 25 kilojoules leaving, and we know the difference in internal energy. We just need to be sure that this difference in internal energy is accounted for with the 3 kilograms of mass, because or else our units are not going to be correct. So what we need to do is, let's do the difference in internal energy using the values that we have. We have 2340.71 minus, that's state 2, and state 1 is 2852.5. which is negative 512.4. Okay, and that's kilojoules per kilograms, and the only reason why I need to eliminate this kilogram is so that I can relate to the heat, because the heat is not in the same units, right? So therefore, if I want to get delta U, do this, I'll just multiply my small delta U by the mass, which is the 512.4 times the 3 kilograms. That allows me to eliminate the kilograms here, and I'm left with negative 1537.2 kilojoules. Okay, so now we need to do some thinking. Okay, we need to think about what's going on to be able to calculate the work, because the calculation itself is super simple, right? You're just going to sum or subtract whatever the two numbers are. But this is where a lot of students go wrong, because if you don't understand what's going on here, you're going to get this wrong. So let's think about the situation. We have our energy scale here. Okay, this is internal energy. And we're going from a higher state of energy into a lower state of energy, correct? So we're starting at 28. So this is our state 1. And we're ending at state 2. So we're dropping like so. And we also know that at the same time we're dropping, we know that heat is leaving. Okay, heat is leaving our system. So if this is the case, well, there's actually 3 possibilities here, right? We may not need work whatsoever. Work may be 0, and work is going to be 0 if the amount of drop in internal energy happens to be the same as the amount of heat leaving, right? We know that's not the case, so this cannot be the case either. So either work is going to be entering or leaving my system. How do we determine that? Well, if the amount of heat leaving is greater than the drop in delta U, then I need work to be going into my system. There's no other option, right? And that takes a form of a compression. If, on the other hand, the delta U is greater than the delta U here, then that means that I need work energy to be leaving my system in the form of work, and that takes form of an expansion. Okay, what is the case? The case is, what do we have? We have delta U dropping by 1500, and we have heat. What's the amount of heat that we have? 2460, right? So heat, let's put heat here. Heat, 2450 kilojoules. Okay, so the amount of heat is greater than the drop in delta U. This can only be possible if there's additional energy going into my system, right? So think about it this way. This guy is taken away. Let's just do the math real quick here. 2450 minus 1537.2. That leaves me with 922.8 kilojoules. So this guy here is taking away 1537.2 kilojoules that is coming from the internal energy of my gas. But it still needs to take an extra 922 from what the problem statement told us. This energy needs to come from somewhere. It's going to come from the work. Okay, so if work's going in, that means that we have a compression happening in my system. Okay, so the way to do this is delta U will be equal to Q and work. Delta U happens to be negative 1537.2 because the state 2 is slower than state 1. Work leaving my system is 2450, and again negative because it's leaving my system. All right, so therefore that means that work is 922.8 kilojoules going into my system, right? Positive going into my system. And positive going into my system means that this is a compression taking place. Okay, and this comes from the definition of work, negative P dV. Okay, so you can work out that this is a compression. So this is the answer to our problem right here. We have 922.8 work in the form of a compression taking place. I hope this was useful. If you have any questions, as per usual, just leave them down below in the comment section. They will be addressed. If this video was helpful, consider giving it a like, and we'll talk soon.